The captain's hand is shaking as he reaches for the emergency blow switch. Not from fear, from carbon monoxide. 13 men unconscious in the reactor compartment. Temperature gauge climbing past 150 Celsius. June 1984, Norwegian Sea, 200 meters down. But that's not why Moscow will never forgive him. K-131 is an Echo 2, a submarine designed to hide one thing above all else. Not its position, not its crew. Something mounted in the hull itself. Something that only exists in blurred satellite photos and defector testimonies. NATO has been hunting for a clear image for 12 years. The cooling loop is dead. The air is turning to poison. And when this boat breaks the surface, it won't be an empty ocean. NATO forces are operating in the area. Perfect weather. Perfect light. Cameras ready. He can save his crew right now. All it costs is letting them photograph what no Western analyst has ever seen up close. The tubes. The configuration. The launcher systems. Everything. His. Fingers hover over the switch. The temperature alarm is screaming. A decision that takes 3 seconds will rewrite the naval intelligence balance for a decade. Earlier that month, K-131 departed Murmansk on a 60-day North Atlantic patrol. Mission: position within cruise missile range of NATO carrier groups. The Echo 2 class carries 8 P-6 nuclear cruise missiles in external tubes running along the hull, each tube 10 meters long. No fairing can conceal their shape from visual reconnaissance. Soviet designers at TSKB-16 Bureau mounted the tubes outside the pressure hull to save internal space. But that decision turned every surface into a potential intelligence disaster. Each tube is a roadmap. Spacing reveals reload mechanism, diameter confirms missile size, hatch configuration exposes targeting electronics. The captain briefs his crew before departure. If we surface within 50 kilometers of NATO forces, they photograph everything. Tube spacing, weld patterns, sensor housings, anechoic tiles. One surface exposure compromises the entire class design. Western intelligence had closely monitored the Echo 2 class for over 2 decades, eager for just such an opportunity. Western analysts know the missiles are nuclear-tipped, but they have never measured the tubes precisely. P-3 Orion patrol aircraft crisscross the Norwegian Sea daily, hunting for Soviet submarines to track. If an Echo 2 surfaces in daylight, cameras will be ready within minutes. The VMA reactors are first-generation pressurized water, prone to coolant leaks and overheating. Available records suggest multiple cooling loop repairs in the months preceding the incident. The chief engineer reports both reactors nominal, but notes starboard primary loop pressure fluctuating. These reactors were designed in the late 1950s, before Soviet engineers fully understood thermal stress on gaskets and seals. The cooling loop operates at 300 degrees Celsius and 180 bar. Any seal failure drops pressure rapidly, and once pressure falls, decay heat from the reactor core becomes a time bomb. Soviet doctrine is clear. If mechanical failure forces surface, head for open water away from NATO assets. But rescue submarines are 800 kilometers away. Response time, 72 hours minimum. Echo 2 boats patrol far beyond the range of rescue vessels. Northern Fleet operations staff calculated the risk and accepted it. Because keeping the boats close to Soviet waters would leave NATO carriers unthreatened. The captain runs the math. Technical estimates for early Soviet reactor designs suggest that without active cooling, compartment temperatures could reach hazardous levels within roughly 30 minutes. No time to run west. He orders the watch officer to log any NATO surface contacts immediately. Hour 36 of patrol, depth 200 meters. Starboard reactor compartment alarm sounds. Primary cooling loop pressure drop. The chief engineer reports a seal failure on the steam generator inlet. Standard procedure is to shut down the starboard reactor, shift load to the port side, and repair underway. The seal is a metal-reinforced gasket that sits between the primary loop piping and the steam generator. Thermal cycling over months of operation causes microcracks. When the gasket ruptures, high-pressure coolant leaks into the generator housing. Pressure drops from 180 bar to 120 bar in 4 minutes. The reactor scrams automatically, control rods inserting to halt fission. Shutdown begins, but there's a problem. Residual heat trapped in the core demands active cooling from the secondary loop. Even with fission halted, the reactor can't simply be switched off. Decay heat from fission fragments continues at roughly 6% of full power, 4.2 megawatts thermal, the heat of 1,000 industrial ovens that cannot be turned off. Backup pumps engage, circulating water through the steam generators, carrying the heat away. But within 8 minutes, smoke detectors trip in Compartment 7. Electrical fire in the turbo generator, source unknown. The turbo generator, already stressed from the reactor shutdown transient, shorts out. Insulation on cable runs ignites. Flames spread along the overhead cable trays. The fire led to the activation of the Freon suppression system. Freon floods Compartment 7, extinguishing flames by displacing oxygen. But combustion has already produced carbon monoxide. The fire consumed oxygen and cable insulation, generating CO that likely reached thousands of parts per million within minutes in the sealed compartment. The damage control team seals the bulkhead doors, but 3 men are trapped inside, trying to extinguish flames before the Freon deployed. CO is slightly lighter than air and begins to diffuse through ventilation ducts into adjacent compartments. The Atmosphere Watch reports rising CO levels in Compartments 6 and 8. The blowers strain against the weight of the ocean, unable to push a single breath of smoke out. At 200 meters down, they're fighting 20 bar of external pressure. A battle they can't win. Submerged venting is impossible. The submarine's air handling system cannot expel toxic gas fast enough without surfacing and opening hatches. The captain orders a partial blow of ballast to reduce depth, buying time. But it's not enough. CO readings in adjacent compartments continue to rise. The chief engineer's report lands like a death sentence. Calculations suggest that if the boat remains submerged, compartment temperature could exceed 180 degrees Celsius within 2 hours, and carbon monoxide will spread through ventilation ducts. There's only one way out. Emergency surface. Open all hatches. Vent for 20 minutes minimum. The captain asks for NATO surface contacts. Sonar reports 2 destroyer-sized contacts to the northeast closing. The watch officer updates the plot. NATO warships are conducting exercises in the area, moving southeast. If K-131 surfaces now, they will arrive quickly. The captain calculates the options. He can wait, hoping the CO levels stabilize. But the chief engineer shakes his head. The men in Compartment 7 are already unconscious. Temperature is climbing. Waiting means deaths. He looks at the sonar plot and understands what surfacing will cost. NATO will photograph every meter of the hull. The missile tubes, the weld lines, the sensor housings, everything. The captain orders emergency blow at 03:42 hours. Main ballast tanks vent compressed air. The submarine's bow angles up 15 degrees. Depth gauge climbs. 180 meters, 120 meters, 60 meters. Surface in 6 minutes. The crew braces against the angle. In the rear compartments, the crew faced rising radiation and heat from escaping steam, leaving some incapacitated. The damage control officer reports no response on the intercom. The captain knows they have minutes, maybe less. The hull groans as the ascent rate peaks at 3 meters per second. The watch officer calls out depths. The captain stands at the periscope well, watching the gauge needle swing upward. Sonar updates. NATO contacts have changed course, closing at 22 knots. The captain calculates intercept. They will arrive within 15 minutes of surface. No time to maneuver away. The boat must vent Compartment 8 immediately, or the crew dies. The watch officer asks if they should alter course after surfacing. The captain says no. We surface, vent, stabilize, and submerge. The NATO ships will see us, But if we maneuver on the surface, we extend the exposure window. Better to stay stationary and finish venting as quickly as possible. He knows it makes no difference. Stationary or moving, the cameras will capture everything. The submarine surfaces at approximately 03:48 hours. The conning tower breaks the waterline, then the hull. Waves wash over the missile tube fairings. The watch officer climbs the ladder and opens the bridge hatch. Toxic smoke pours out, thick and black. He gasps, pulls on his respirator, and scans the horizon. Clear weather, light wind, visibility 20 kilometers. He can already see the NATO destroyers to the northeast, gray silhouettes against the morning sky. The chief orders all compartment hatches cracked open to vent. Fresh air rushes in. The temperature in compartment 7 begins to drop. The men trapped inside are pulled out, unconscious but breathing. The medic starts resuscitation. In the early morning hours, a NATO destroyer appears on the horizon. Minutes later, a British frigate closes to 8 kilometers, telephoto cameras on deck. The captain sees the flash of lenses. Photographers are shooting from the bridge wings and signal decks. His weapons officer asks if they should prepare to dive. The captain says no. Compartment temperature is still 140 degrees. CO levels lethal. We have no choice. For a period of time, K131 sits stationary on the surface, while auxiliary diesels pump fresh air below. NATO ships circle at 5-kilometer range, photographing the hull from bow to stern. Every missile tube hatch, every weld line, every sensor housing. The captain counts the camera flashes and knows the damage is done. The VMA reactor uses pressurized water at 300 degrees Celsius in a closed primary loop. The loop circulates through the reactor core, absorbing heat from the fuel rods, then flows into steam generators where it heats a secondary loop that drives turbines. The secondary loop is at lower pressure and remains isolated from the radioactive primary coolant. The primary loop operates at 180 bar to keep the water liquid at 300 degrees. Seals at the steam generator inlet are the weakest point in the system. Thermal cycling during reactor startup and shutdown causes micro cracks in the gasket material. Over months of operation, these cracks widen until the gasket ruptures. Starboard seal failed, the clock started. Primary coolant pressure plummeted from 180 bar to 120 bar in 4 minutes. High-pressure coolant gushed into the steam generator housing. The reactor safety systems detected the drop and scrammed automatically, slamming control rods down to halt the fission chain reaction. But here's the problem. Stopping fission doesn't stop the heat. Decay heat from radioactive fission fragments continues at roughly 6% of full power output, 4.2 megawatts thermal, enough to melt the core if it's not removed continuously. The secondary cooling loop can handle this load, but only under one condition. The turbo generators must stay online. The secondary cooling loop pumps engage to circulate water through the steam generators, carrying decay heat away. But the turbo generator in compartment 7, already stressed from the reactor shutdown transient, shorted out. Electrical current surged through the generator windings, overheating the insulation. The insulation ignited, and flames spread along overhead cable trays. According to technical reconstructions of the incident, the fire consumed oxygen and produced carbon monoxide at potentially lethal concentrations in the sealed compartment, with levels possibly reaching as high as 2,000 parts per million per minute. The Freon suppression system extinguished the flames within 90 seconds, but by then, the damage was done. The compartment atmosphere was toxic, and 3 men inside had already lost consciousness. Carbon monoxide is slightly lighter than air and began to diffuse through ventilation ducts into adjacent compartments. The submarine's ventilation system is designed to circulate air and equalize pressure, but it cannot filter or remove toxic gases while submerged. CO levels rose in compartments 6 and 8 within minutes. Atmosphere monitors sounded alarms. The damage control team sealed bulkhead doors to slow the spread, but the ventilation ducts remained open. Closing them would eliminate airflow and cause rapid pressure and temperature rise throughout the boat. The crew faced a choice: let the gas spread or suffocate from lack of ventilation. According to crew accounts, submerged survival under these conditions was estimated at less than an hour. Submerged venting requires expelling contaminated air and drawing in seawater-filtered air through snorkel intake. But at 200 meters depth, external pressure is 20 bar. The internal compartment pressure is roughly 1 bar. The ventilation blowers are designed to move air against small pressure differentials during normal operations, but they cannot overcome a 19 bar difference. To expel gas, the blowers would need to push air out against 20 bar of external water pressure. The system lacks the power. The only way to equalize pressure and vent the compartment is to surface, where internal and external pressure are equal, and atmospheric convection can flush the toxic air out through open hatches. The captain stares at 3 instruments: temperature gauge, CO monitor, sonar plot. Stay submerged. The crew faces suffocation in what could be as little as 90 minutes. Surface. NATO photographs every classified detail. He looks down at the blueprints spread across the navigation table. His finger traces the reactor cooling system, then the ventilation system. They don't connect. They can't connect. The VMA reactors, built in the late 1950s, were designed for compactness and power output, not fault tolerance. The engineers assumed reactor casualties would be rare. They assumed submarines could always reach shallow water before venting became critical. But there is no shallow water. Not here. Not now. The captain's hand hovers over the blueprints. He's searching for something that was never drawn. A plan B for this depth. An emergency pathway that doesn't exist. The reactor cooling system and the ventilation system are mechanically incompatible with deep emergency venting. The submarine was designed to operate at depth, not to survive catastrophic failures at depth. That assumption was wrong. He looks back at the gauges, the temperature climbing, the CO climbing, the sonar plot showing NATO ships above. Physics has already decided. He just has to accept it. At 0418 hours, compartment temperature drops below 80 degrees Celsius. CO levels fall to 200 parts per million, breathable with masks. The damage control team re-enters compartment 7 and confirms the fire is out. Electrical systems are fried. The starboard turbine is offline. Cables are scorched black. Insulation melted. The turbo generator housing is cracked from thermal stress. The chief engineer reports the starboard reactor cannot be restarted without dockside repairs. K131 is now running on 1 reactor. Maximum submerged speed reduced to 12 knots. The captain orders the compartment ventilated and atmosphere continuously monitored. The captain orders hatches sealed and ballast flooded. Dive time, 4 minutes to periscope depth, then level off at 60 meters. The NATO destroyers are still circling at 5 kilometers, but Submerged the submarine is invisible again. The captain feels the hull angle down and knows it is too late. For a critical period on the surface in perfect light, the cameras captured every detail. The missile tube spacing, the weld patterns, details of the hull's construction, the sensor housings on the sail. NATO analysts will measure, compare, and estimate. They will know the missile diameter, the reload mechanism, the structural weak points. The captain's report will say he saved the crew. Moscow will ask why he surfaced in NATO-patrolled waters. The captain surfaces briefly 40 minutes later to extend the radio antenna and transmit a contact report to Northern Fleet headquarters. Message: Reactor casualty, emergency surface, NATO visual contact confirmed. According to available records, he requests permission to continue patrol on 1 reactor. Fleet Command responds within 10 minutes. Return to Murmansk immediately. No further transmission. The captain copies the message and orders the radio operator to secure the antenna. He knows what the order means. The mission is over. The submarine is compromised. The patrol is a failure. He will return to base and face the Board of Inquiry. His crew survived, but the intelligence loss will be measured for years. The executive officer asks what happens now. The captain stares at the photographs. NATO has it all. The missile tubes, the sensor array, the hull coatings. But here's what breaks him. Analysts will count tile rows to assess acoustic stealth. One surface, one set of photographs. And suddenly NATO knows the exact sound signature of every Echo 2 submarine in the fleet. The intelligence advantage built over 12 years of operational secrecy is gone. If they know where to listen, every boat in the class is already being tracked. The submarine limps east on one reactor, maximum submerged speed 12 knots. The captain orders continuous ventilation of all compartments and posts extra atmosphere watchstanders. He writes the incident report in his cabin. The Board of Inquiry will ask why he surfaced in NATO-patrolled waters. The answer is simple. Because the reactor failed and the crew would have died. There was no other choice. According to accounts of the incident, he emphasizes this point repeatedly in the report, knowing the men survived, but the mission failed. The submarine is compromised. The rest is beyond his control. He signs the report and seals it for delivery to Fleet Command. 131 arrives at Vidyayevo Naval Base on June 26, 1984, escorted by a tug. The crew disembarks for medical evaluation. Survivors are treated for carbon monoxide exposure, though the fire itself had already claimed 13 lives. The captain is summoned to Fleet Headquarters. The Board of Inquiry convenes within 48 hours. Questions focus on the decision to surface within NATO visual range. Could he have maneuvered farther west before surfacing? Could the crew have waited longer submerged? The captain repeats the timeline. Seal failed, fire started, CO spread, venting was impossible at depth. The crew had 90 minutes maximum submerged. According to tactical reconstructions, NATO ships were approximately 35 kilometers away when the decision was made. The board takes notes. Historical records suggest Captain Selivanov's seagoing career effectively ended after the investigation. He would not receive another command. The Soviet submarine commander has no idea what's coming. At Northwood, NATO intelligence analysts process 127 photographs from the June 18th incident, and what they find changes everything. Missile tube spacing, 3.2 meters center to center. Tube diameter, 1.4 meters, confirming P6 missile dimensions. But it's the weld lines that tell the real story. A double hull structure with external tube fairings bolted, not welded. Maintenance access points, weak points. Each photograph is cataloged, measured, cross-referenced with previous intelligence on the Echo 2 class. The analysis takes 6 weeks, but when the report lands, it's devastating. The submarine's missile system and hull structure are now fully characterized. Western targeting doctrine is updated accordingly. Every Echo 2 in the Soviet fleet just became vulnerable. Anechoic tile patterns are mapped in detail. Intelligence reports suggest approximately 18 rows of tiles, each roughly 0.6 meters square, covering an estimated 60% of the outer hull. Gaps in the tile pattern near the sonar dome and propeller shaft indicate acoustic weak spots. The tiles are designed to absorb active sonar pings, reducing the submarine's acoustic signature. But the gaps reveal where Soviet engineers prioritized structural access over stealth. NATO sonar operators are briefed on the weak spots. Future tracking exercises will focus active sonar on those areas, where the Echo 2 hull reflects sound most strongly. The intelligence advantage shifts measurably. Sensor housings on the sail are photographed in profile, revealing antenna geometry for targeting radars. The housings are cylindrical, mounted in pairs on the forward face of the sail. Analysts estimate antenna diameter and calculate radar frequency range from physical dimensions. The P6 missile requires mid-course guidance updates from the submarine, transmitted via these antennas. Knowing the antenna geometry allows Western electronic warfare systems to jam or spoof the guidance signals. According to intelligence community accounts, countermeasures were reportedly developed and tested in a remarkably compressed time frame, possibly as little as 8 months. The intelligence from one surface exposure enables tactical countermeasures across the entire NATO fleet. The Soviet Navy conducts a fleet-wide review of VMA reactor reliability. Data shows Echo 2 boats suffered 14 reactor-related casualties between 1976 and 1989. 6 resulted in emergency surfaces near or within NATO-patrolled waters. The pattern is clear. The VMA cannot be trusted for extended patrols in hostile areas. The review recommends accelerated replacement of first-generation reactors and redesign of cooling loop seals. But funding is limited, and the Echo 2 class is already obsolescent. The decision is made to decommission the boats rather than invest in refits. Engineering failure drives strategic policy. By 1989, the decision to decommission the Echo 2 class accelerates. Official rationale? Obsolescence and budget constraints. Unofficial factor? The boats have been photographed so many times that their design is an open book to NATO. The mass decommissioning of the class began in earnest in 1989. The last is decommissioned in 1994. Some hulls are scrapped, others are moored as storage hulks. K-131 was decommissioned in 1991, though its full scrapping process took several more years. The submarine that surfaced into NATO cameras serves out its final years rusting at a northern base, its missile tubes empty, its reactors cold. Mechanical failure ended the class as surely as any weapon. The captain of K-131 is reassigned to shore duty and retires in 1987. He is never given another command. In post-Soviet interviews, he defends the decision to surface. The reactor failed. The crew was dying. I could not stay submerged. If that meant NATO saw everything, so be it. The machine left me no choice. His words are matter of fact, no bitterness. Tragically, 13 men lost their lives in the fire that day, though his decision to surface likely saved the remainder of the 90-man crew. The intelligence loss was not his failure, it was the reactors. The Board of Inquiry noted his decision was procedurally correct. But procedural correctness does not erase strategic consequences. He retired quietly and disappeared from the naval record. The Echo 2 surfaces again and again. Each time NATO cameras are waiting. Western analysts would later calculate the intelligence value, equivalent to years of covert collection. One submarine's mechanical failure handed them the design specifications they've been hunting since 1972. The failures of the Echo 2 class became a cautionary tale often discussed in Soviet naval circles. The lesson? When engineering fails, operational security is the first casualty. No amount of crew discipline or tactical skill can compensate for a reactor that forces you to surface in hostile waters. But the real lesson runs deeper. The VMA reactor was designed for power and compactness, not fault tolerance. That choice, made in the late 1950s by engineers under pressure to match Western submarine performance, defined the operational limits of an entire class. The machine defines the mission. When the machine fails, the mission fails with it. Somewhere in a Soviet scrapyard, an Echo 2 hull sits, cut open to the air. Its reactor compartment exposed. Its secrets already photographed, cataloged, understood. The submarine that was supposed to stay hidden became the most visible boat in the fleet. An open book, spine cracked, pages turned by enemy hands.